So the last section in this chapter is about something called improper integrals. Improper integrals. So up until now, we have only been talking about, up till now, we've only we've been limited to continuous functions on bounded intervals. Right, you have some closed and bounded intervals. Right, you have some function on AB, right? And then and it's a continuous function, right? So you have some continuous function on AB, and then you get the integral. You get the integral of it, maybe by finding the antiderivative, or in this last section we talked about getting approximations of the integral. Okay, so these things are called proper. These things are called proper integrals. Proper integrals, and there are two ways. So an integral can be improper in two ways. And it could be in both of these ways. I'm seeing you. Is there something you can't read? No? Proper integrals. An integral can be improper in two ways. One, either the function could be unbounded, or the interval of integration is unbounded. So those are the two things can happen, right? You could have when we're talking about improper integrals, you could have a function and you're looking at the integral of that function from a to infinity, right? So you have some function that goes like this, right? And you're wondering how to say something about the area under this infinite object. Right, it goes on forever. Okay, so that's possibility 2, and then possibility 1 is you have some function, and maybe it's okay over here, but it has some asymptote as you approach b. Okay, so it goes off toward positive infinity, or maybe it goes off towards negative infinity. Okay, and again, you're curious about what you can say about this integral. So you can probably figure out what we're going to do, right? How are we going to extend the notion of integral? Well, we're just going to we'll deal with these with improper integrals by defining them as the limit of proper integrals. Okay. We'll define them as the limit of proper integrals, right? So, for example, right, here's this thing that goes on forever. So here's this integral that goes on forever, right? You don't know how to deal with it, but you do know how to take this integral, right? You do know how to take this integral, and so you calculate that integral, and then you let b tend towards infinity, right? So for this sort of integral, right, when we talk about the integral from a to infinity of f, what we mean is the limit as b goes to infinity of the proper integral of f from a to b. Okay, right? That's a pretty natural thing to do, right? That's a natural thing to do. Okay. Similarly here, right? We don't really know what it means to take the integral from a to b of this guy, but we'll do the same thing. We'll say the integral from a to b of f will be the limit as c goes to b from the left-hand side of the integral from a to c. Right? Does that make sense? That makes sense? That's sort of like what the obvious thing you would do, right? You don't know how to take this integral, but you do know how to take these integrals, right? And so you take these integrals, and then you let c tends towards b from the left-hand side, right? And you get some number. If you get some number, then you say that the integral equals that. So yeah. So maybe I should put that formally down. We define the integral from a to infinity as the integral from the limit of the integral of a to b as b goes to infinity. And if this limit exists, we say the integral is convergent. Convergent integral. If it doesn't, if not, we say it's divergent. If not, we call it divergent. And then we do a similar definition for functions that have asymptotes, right? If the limit of f as x approaches b is infinity, we define the integral from a to b of f as the limit of c as b goes to b from the left-hand side of a to c f of t dt. Okay, and the same thing. Right? If this limit exists, we say it's convergent. If the limit doesn't exist, then we say it's a divergent integral. So we deal with these infinite integrals by defining them to be the limit of the finite integrals. Sort of an obvious thing to do. Okay, any questions? Any questions? What do you think? It's a simple idea. What you should feel probably at this point is that it's nothing so spectacular. It's not. So let's do some examples. Okay. So suppose I ask you to evaluate the integral of 1 over x from 1 to infinity. Okay. You've got the 1 over x function. You've got the 1 over x function, and I'd like to know the area, from here onwards. Okay. Well, what's going to happen? The way we define this, right? We define this to be the limit as b goes to infinity of the integral from 1 to b of 1 over x dx. Okay. So you get, right? the limit as b goes to infinity of the natural log of b minus the natural log of 1, which is 0. Okay. Well, what's that? As b goes to infinity, natural log of b is, as b goes to infinity, natural log of b goes where? What happens to it? Infinity, right? So you get infinity, right? And so we say that this is a divergent integral. So the integral diverges. Right, so the limit, okay. Maybe I should make it clear if the limit is finite. Right, we don't want any. We don't call it convergent if it's infinite. Okay. Okay, so that's example 1. Example 2. Suppose I ask you to integrate from 0 to 1 over x dx. Okay. So again, now we're asking about this area here. Right? We're asking about this area here. What's that area? Take 1 minute and write down the answer, or just 10 seconds and write down the answer. Okay, talk to somebody, turn to somebody nearby and talk with them. Okay, who would like to say? Who would like to say what's going on? Anybody? Yeah, go ahead. Infinity, yeah, exactly. You get infinity again, right? Because you're going to take the limit as a goes to 0 from the right-hand side of the integral from a to 1, right? You're going to take the right? Again, the infinite occurs as you go to the left, right? So we're going to let a go to the left, right? You get 1 over x dx. Again, you get the limit as a goes to infinity, or a goes to 0 plus, of the natural log of x between a and 1, right? So you get right, 1 minus the natural log, I'm sorry, 0 minus the natural log of a, right? As a goes to 0 plus, right? But as a goes to 0 plus, the natural log goes to negative infinity, right? Remember what the natural log looks like. Natural log looks like this. Okay. As a goes to 0, natural log of a goes to negative infinity. Right? Natural log is the reflection of the exponential function. Right? It's the reflection across the y-axis, across the line y equals x. Right? They're inverses of each other. Right? So you get, turns into positive infinity. So again, it's divergent. So it's divergent. Okay. Okay, let's see. How about, so here's another exercise for you. The integral from 0 to infinity of x squared e to the minus x cubed dx. Okay. So the x squared term is increasing. The e to the minus x cubed term is decreasing. Very fast, in fact. Right? Okay. I'm going to ask people to guess. What do you think is going to happen? Will it be convergent or divergent? What do you think? You get a finite number, or do you get some infinite number? Who votes for it's a finite area? Who votes that it's going to be finite? Finite. Who votes for infinite? Okay. I actually like to hear you talk. Those of you who say it's infinite, why do you think it's infinite? Why do you think it's infinite? What intuitively says to you, this is going to be an infinite thing? Yeah.
I'm not sure about this infinity.
There's an infinity in there, yeah? Yeah. So, I mean, there's a couple of infinities, right? One is that we're integrating all the way to infinity, right? We're integrating all the way to infinity. And then there's also this infinity. X squared goes to infinity, but we're multiplying it by e to the minus x squared. Right? Those of you who say it's finite, why do you say? There are 3 people who said it's finite. Why? You change your mind. You think it's infinite. Okay. There's only 2 people who say it's infinite. I'd say it's finite. Okay. So why do you think it's finite? Why do you 2 think it's finite? Just guessing? Just guessing, or some intuition? Okay, let's do it. So, right, so we're gonna take the limit as b goes to infinity of the integral from 0 to b x squared e to the minus x cubed, right? How do you integrate it? U substitution. What are you going to take as your u? X cubed. Okay, so we'll take u to be x cubed, right? Or maybe negative x cubed. It doesn't matter. Du is going to be negative 3x squared dx, right? And so we get the integral. We get the limit as b goes to infinity of the integral from 0 to b of negative 1/3 du, and then e to the u, right? U substitution, right? And so you get, what am I doing? It's not between 0 and b, right? It's not between 0 and b. When x is 0, u is 0, right? When x is b, u is negative b cubed. Okay, and so we get the limit as b goes to infinity, and maybe I'm going to no, I'm going to do that. Okay. So you get negative 1/3 e to the u between 0 and negative b cubed. Right? In other words, negative 1/3 e to the negative b cubed minus e to the 0 as b goes to infinity. Right? Anyone confused by this? Anyone have some stuff that you don't get? The b cubed. Can somebody tell Wang Bo how we get the b cubed? How do we get the b cubed? Hong Dong, how about you? Can you tell? Yeah, where does this b cubed come from?
It's
From the x. It's actually from the substitution.
Yeah.
Right, from this x cubed here. This is x cubed. Did you say x squared or x cubed? It's x cubed. Yeah. Okay. So so when x is 0, u is 0. Right. When x is b, u is negative b cubed. Right. So. Huh? Sorry, that's a 3. It's a very sloppy looking 3. Sorry. It's okay now, I hope. Okay. Sorry. Okay, now it's okay. That was actually a 3. Okay, so what happens, right? When b goes to infinity, what happens to this term? You get e to the negative b cubed as b goes to infinity. What is it? 0, right? Right. That's going to be 0, right? 1 over e to the b cubed as b goes to infinity. That's going to be 0, right? Okay, so that goes to 0, and we end up. This is 1, of course, and we end up with 1/3. So those of you who said it was finite, you're actually right. It is finite. Yes.
Does that intuition work most of the time?
What intuition?
Like, I said it would be infinity simply because I saw the infinity in the original question.
Yeah. So clearly that did not work, right? It turned out to be a finite number, right? So maybe the way you want to think is like this: x squared is increasing. Certainly, x squared is increasing, but e to the x is a very, very fast function, right? If we're looking at e to the x, and you probably have seen this in L'Hopital's rule. You've seen L'Hopital's rule? People seen L'Hopital's rule? Anyway, e to the x is faster than any polynomial, right? And here we have e to the negative x, so it's going to be decreasing extremely fast, right? It's going to be approaching 0 extremely fast, right? So the way you think is that probably the e to the negative x cubed is going to make the integrand shrink a lot faster than the x squared is going to make it grow. And so you think that probably it's going to be finite. Let's see. Okay, so I want you to do another problem, which is this: 1 over x to the p dx. Okay, but p is some number. I want you to tell me, is this, for what p, is this convergent? Right, for what p is this integral convergent? Okay, so work it out and see what happens. Okay. we already know that, so p will be not equal to 1. So p not equal to 1. We already know that when p equals 1, this is divergent. So we don't need to do that again. Okay, again, turn to somebody nearby and talk with them. Can I shout out the window? Like, okay, who would like to say? Who would like to do it? Who would like to do it? Anybody? Right, you get the limit as b goes to infinity, 1 to b, right? X to the negative p dx, right? What's the integral? What's the integral? They're actually right. Somebody has parked blocking a bus, so the bus is trying to get their attention. So I'm not going to shout at them. Right. So right. So you get x to the negative p plus 1 over negative p plus 1, right? Between 1 and b. That goes to infinity. Right. Okay, so what happens, what do you get? right? You get b to the 1 minus p over 1 minus p minus 1 over 1 minus p. As b goes to infinity. Right? So what happens? For what p do you get a finite answer? For what p do you get a finite answer? P bigger than 1, right? If p is bigger than 1, then this b to the 1 minus p as b goes to infinity is going to be 0, right? So that term will vanish, and you'll end up with minus 1 minus p. Right? Plus 1 minus p. Right? No, minus 1. Right, so yeah, so p is going to be bigger than 1, and then this will be a positive number. Okay. And if p is less than 1, then you're in trouble, right? Because you'll get b to the you get b to some positive power as b goes to infinity. Then you get infinity, right? So it converges for p bigger than 1 and diverges for p less than or equal to 1. Okay. A similar problem. Suppose I ask you the integral from 0 to 1, 1 over x to the p dx again, right? And I say what range of p works, right? What range of p gives you a convergent integral? What do you think? Can anyone guess what the answer is? The inverse solution, so they're the opposite, right? So that when p is smaller than 1, right, then right, if p is bigger than 1, that means that this thing is going to grow really fast, right? This thing is going to grow really fast, right? But if p is smaller than 1, then this thing is going to grow a bit more slowly. It's still going to grow, but it's going to grow more slowly. Okay, and it turns out that 1 is again the boundary. Okay, yeah, so the opposite answer is correct, right? Right, because what you're going to get, of course, is the same sort of thing. The limit as a goes to 0 plus of 1 over it's going to be x to the 1 minus p over, again, 1 minus p between a and 1. Right? So you get the limit as a goes to 0 plus of 1 over 1 minus p minus a to the 1 minus p over 1 minus p. Right? And if p is bigger than 1, then you're in trouble, right? If p is bigger than 1, as a goes to 0, this thing is going to become infinite. So if p is bigger than or equal to 1, then you have divergence. If p less than 1, then you have convergence. Okay, any questions? Okay. Okay. You can also have, you can also have this sort of problem. So, sort of a combination problem, dx over x minus 2 to the 1/2. Okay. You see what the trouble is, right? When x is equal to 2, the function blows up. Right? The function goes to infinity. So this is one of these things where there's an asymptote in the middle, right? I should say maybe the absolute value of x minus 2, because otherwise you'd be talking about the square root of negative numbers. In any case. Okay. So, so this is some sort of function that blows up like this, and you just express it as two integrals, right? You express this thing as two improper integrals. You know, the first one goes from 1 to 2, and the second one goes to 2 to 3, right? So from 1 to 2, plus the integral from 2 to 3, and you have to say the limit as b goes to 2 from the left, plus the limit as b goes to, as a goes to 2 from the right, 1 to b, and from a to 3. Okay. So anyway, that's